So we're going to look at, in this video, we're going to look at spontaneous processes versus temperature. This is page 916 in your textbook. And this is kind of going to pull all of the stuff we've been talking up to this point about our Gibbs energy calculation. So delta G is equal to delta H minus T delta S. In one of the other videos talking about combustion of propane, we looked at how the entropy change of that reaction was negative, yet the Gibbs energy, it's still a spontaneous reaction. So the Gibbs energy must be negative. So we had to reconcile that even though the delta S was negative, so that goes against what the universe wants to do, there was something happening that makes delta G negative. And that comes back to talking about delta H, which is the opposite of the entropy gained by the surroundings or lost to the surroundings. So we're going to look at that in a little more detail and talking about 4 different cases how temperature affects the Gibbs energy change. So the first case is that some reactions are spontaneous at all temperatures. So some reactions that are spontaneous at all temperatures, if we look at our delta G minus delta H, or delta G is equal to delta H minus T delta S, this means all temperatures, that's basically anything greater than 0 Kelvin. So no matter what temperature it's at, it's going to go forward. So the combustion of propane is a good example, or another one we can look at here is the decomposition of hydrogen peroxide. So this is why hydrogen peroxide has an expiration date, so that hydrogen peroxide in your cabinet may not be working very well after too long, because eventually it will decompose spontaneously into 2 moles of liquid water and oxygen gas. So after a while, your bottle of hydrogen peroxide is just water and oxygen. The enthalpy change of this reaction is negative 196, so it's exothermic, gives off heat, and the entropy change is a positive 125 joules per Kelvin. And so it's gaining entropy because it's making a mole of gas from a mole of liquid, and it's exothermic because we're breaking some bonds and forming less energetic bonds, so it's giving off some of that heat to the universe. So if we go back up here to our delta G reaction, we have a positive delta S and a negative delta H. So we have negative minus a positive, so this whole term becomes negative. So no matter what the temperature is, it could be 1 Kelvin, it could be 1,000 Kelvin, no matter what, delta G is only going to get more negative. So this is an example where it's spontaneous at all temperatures because delta G is always negative. It doesn't matter what the temperature is, it has to be greater than 0K obviously, but anything greater than 0K, 1K, 1000K, anything like that, is still going to produce a negative delta G, so it's always going to be spontaneous. The opposite of that is it's non-spontaneous at all temperatures. And so you might be thinking, well, if it's non-spontaneous at all temperatures, then the reaction doesn't happen. That's not entirely true. It means we just have to put some energy into the reaction to get it to go forward. So there's nothing we can do temperature-wise to get it to just happen spontaneously, but we can put energy in and drive it forward. So a classic example of that is the decomposition of oxygen into ozone. This is what happens in the upper atmosphere when high energy ultraviolet rays from the sun strike our atmosphere and they hit molecules of oxygen in the upper atmosphere and form 2 moles of ozone. So we have to put energy in, so this is an endothermic process. The enthalpy of this is a positive 286 kilojoules. So we have to put in energy, and that comes from the form of ultraviolet rays from the sun in order to drive this process. And the entropy, since we're taking 3 moles of gas and making it into 2 moles of gas, we should be losing entropy, and we are. It's negative 137 joules per Kelvin. So again, going back to our delta G, delta H minus T delta S. Again, T is always going to be greater than 0, but what we have here is we have a negative delta S and a positive delta H. And since we have a negative and a negative here, oop, that looks terrible. We have a negative and a negative, this is going to be positive, so it doesn't matter what T is. It could be 1 Kelvin, it could be 1,000 Kelvin. This delta G is always going to be positive. There's nothing that can be done to undo that. It's always going to end up positive. So delta G, when delta G is positive, we have a non-spontaneous reaction. So again, it's not that this reaction doesn't ever happen, it's that we need to put energy into it to drive it forward. There are two more cases that do depend on temperature. So reactions that become spontaneous at higher temperatures. So we'll just say at high temp. And I'm going to be very vague here because, as we're going to see in a moment, that there's actually a certain temperature when these types of reactions can switch from spontaneous to non-spontaneous. So we're just going to be vague and we're going to say at high temperatures. A classic example of this is the decomposition or the reaction of dinitrogen monoxide and oxygen into nitrogen monoxide. This is an endothermic reaction with a positive 197.1 kilojoules for the enthalpy. And the entropy, it's also gaining entropy. We're taking 3 moles of gas and forming 4 moles of gas, so we are increasing the entropy in this case. So if we go back to our Gibbs energy equation, we have a positive delta H, so we're already off to a bad start because the enthalpy is positive, which means we have to put heat in, which means Gibbs energy would be positive. The only thing that can overcome that is if this T delta S term becomes more negative than the positive term. And the only way that that happens is when we're at high temperatures. So in order for this is a negative term, but that negative term has to be greater than the positive delta H term. So what we end up saying is that temp must be large enough for T delta S to be greater than delta H, so that delta G can be less than 0. Another example of this, just to kind of make it a little more intuitive, and we don't even have to use any data, we kind of know this one already, is the melting of ice. So solid water melting. So this doesn't just apply for chemical reactions, it also applies for physical changes. So we like to use the word processes, so this is a spontaneous process. So the melting of ice, we know that this becomes spontaneous, delta G is less than 0, when temperature is greater than 273.15 Kelvin, or 0 degrees Celsius. We would be very surprised to watch ice melt when it's less than 0 degrees Celsius. So if we were standing outside and it's negative 20 degrees Celsius outside, and we watched a block of ice melt, we would be very surprised that would just be happening spontaneously because it's too cold for that to happen. This only becomes spontaneous above a certain temperature. For the case of water, that becomes 0 degrees Celsius. And the fourth case is that some processes are spontaneous at low temperatures. So one example of this is the formation of rust from iron. Iron plus 3 moles of oxygen become 2 moles of iron oxide, which is just rust. This has an enthalpy of reaction. It's exothermic, negative 1651 kilojoules per mole. It's very exothermic, but it just happens so slowly we can't notice it on a day-to-day scale. And the entropy is also negative. We're taking, well, that shouldn't be solid, it should be gas. We're taking a gas and forming more solid, so we're decreasing the entropy. This is negative 549.4 joules per Kelvin. So again, back to our delta G is delta H minus T delta S. In this case, we have an exothermic reaction, so that's fairly favorable. However, we also have a decrease in entropy, so again, that's not favorable. So when we take these two terms together, they become positive. So in this case, we want the temperature to be very low or very small so that this positive number between the two terms is a small positive number, so delta H can make delta G negative. So we want delta G to be negative in this case to make it spontaneous, but the T delta S term has to be small. So we say temp T must be small enough for the T delta S term to be less than delta H, so that delta G will be less than 0 again and become spontaneous. And again, just a more intuitive example we probably already know is the reverse of ice melting. It's ice freezing or water freezing. So water will freeze spontaneously at low temperatures to become solid ice. And again, this is spontaneous, delta G of less than 0, when the temperature is less than 273.15 or less than 0 degrees Celsius. So in the previous example, we would say that we'd be very surprised if solid ice would melt below 0 degrees Celsius. And in this case, we would be very surprised that if a puddle of water turned into ice when we're at room temperature, which is greater than 0 degrees Celsius. So that 0 degrees Celsius is important for water because that's the temperature at which it switches from being spontaneous to non-spontaneous in terms of talking about which process is which. So they're kind of going back and forth. The water would melt above 0 degrees Celsius, so the melting process would be spontaneous, whereas the freezing process would be non-spontaneous above 0 degrees, and its opposite below 0 degrees. Below 0 degrees, the freezing becomes spontaneous and the melting becomes non-spontaneous. So we can calculate the temp when a reaction becomes spontaneous. We call it the crossover temperature. It's when delta G goes from being greater than 0 or non-spontaneous to delta G being less than 0 or spontaneous. And so it happens in the intermediate between those two. It happens when delta G is equal to 0. So we go back to our equation and say, with our delta G, delta H minus T delta S, we plug in 0 for delta G. This becomes 0 is equal to delta H minus T delta S. We rearrange this to solve for the temperature at which delta G is 0. So I'm going to add T delta S to both sides. And then divide by delta S to solve for the temperature. So the crossover temperature is simply just delta H divided by delta S. So let's just work through a quick example. This is example 20.8 in the textbook. If we look at the decomposition of copper 1 oxide into 2 moles of solid copper, so it's going from a +1 oxidation number to a 0 oxidation number, and we generate half a mole of oxygen. At 298, this has a Gibbs energy of positive 8.9, so it's non-spontaneous at room temperature because it's a positive Gibbs energy. And I also need to supply the delta H for this. It's endothermic, 58.1 kilojoules per mole. And delta S is a positive 165 joules per Kelvin. So if I want to find the temperature at which this does become spontaneous, we can just solve for T is 58.1 kilojoules per mole, and we're going to convert this into joules. So there's 1,000 joules for every 1 kilojoule, And we're going to divide that by delta S, which was 165 joules per Kelvin. So if we just look at all the units that cancel out here, kilojoules cancels kilojoules. And I guess I should have dropped the mole term. It's not going to matter here. And joules cancels joules, and we'll end up with Kelvin as our final answer, which is good. It's what we should end up with. This ends up being 352 Kelvin. So a little bit more than about 80 degrees or so higher than room temperature. And so the temperature at which this reaction would finally become spontaneous would be 352 Kelvin. So we'd take some copper oxide and heat it up to 352 with some oxygen around, or without oxygen, and it would spontaneously decompose into copper and oxide. And this is one way that they isolate copper from its ore of copper oxide.